Welcome to MarkScheme. Transformations of graphs. Everything you need made visual. Here's a single curve. Call it y equals f of x. Just one shape. But watch what happens when we stop treating it as fixed. We can slide it, flip it, and stretch it. And every one of these new curves comes from that same f of x, with a tiny change to its equation. So instead of memorizing dozens of graphs, you learn one, plus the handful of moves in this video. This is the chapter that ties all of functions together. Here's exactly what this covers, straight from your syllabus. Analysis and approaches, standard level 2.11. Translations, sliding a graph. Reflections, flipping it. Stretches, scaling it. And composite transformations, where we combine several moves and ask whether the order matters. Every one of these is on your standard level paper. None of it is higher level only. It leans on graphs and their key features from 2.3, and on the vertex form of a quadratic from 2.6, which, as you'll see, is really just a transformation in disguise. Let's put the whole idea in one picture. In faint blue is our base curve, f of x. In gold is a transformed version, and this equation controls it. G of x equals p times f of q, bracket x minus a plus b. 4 dials, a, b, p, and q, and 2 flips. Watch each one move the gold curve, and keep your eye on where the change sits in the equation. First, b. It's on the outside, added after f. Turn b up, and the whole curve rises. Turn it down, and it drops. Outside means it acts on y, exactly as written. Plus b moves up by b. Now a on the inside, next to x. You'd guess minus a moves it left, but no. F of x minus a shifts the curve to the right. Inside does the opposite of how it looks. Now the 2 flips. Reflect in the x-axis. A minus sign on the outside. And the hill turns into a valley. Reflect in the y-axis. A minus sign on the inside, on x. And it flips left to right across the vertical axis. Finally, the stretches. P on the outside stretches vertically. Crank it to 2, and the curve becomes twice as tall. A vertical stretch, factor p. And q on the inside scales, x, but reciprocally. Q equals 2 squashes it horizontally to half the width. A horizontal stretch of factor 1 over q. Outside as written, inside the opposite. That single sentence is the whole video. Now let's earn it, one move at a time. Start with the gentlest move, a translation, which just slides the curve without changing its shape. Adding b on the outside is the intuitive one. Plus b lifts the whole graph up by b units. Minus b drops it down. Outside the function, it acts on y exactly as it reads. Now the one that trips everyone up. F of x minus a. Your instinct screams, minus, so move left. But it moves right by a. Here's why. To get the same height the original had at x, you now have to feed in a value that's a bigger, to cancel the minus a inside. Bigger inputs are further right, so the whole picture shifts right. Inside the function does the opposite of what it looks like. Minus means right, plus means left. Next, reflections. And the outside-inside rule handles these two. A minus sign on the outside, minus f of x, negates every y value. Every point above the x-axis drops the same distance below it, and vice versa. So our hill flips into a valley. That's a reflection in the x-axis. A minus sign on the inside f of minus x, is different. It swaps left and right. Whatever the curve did at x, it now does at minus x. Our hill, which peaked to the right of the y-axis, now peaks the same distance to the left. That's a reflection in the y-axis. Outside flips top to bottom. Inside flips left to right. The opposite axis to the one you'd guess. The last move is a stretch, which scales the curve toward or away from an axis. Multiply on the outside, p times f of x, and every y value is multiplied by p. With p equals 2, every height doubles. The peak climbs from 2.2 to 4.4, while points on the x-axis stay put. That's a vertical stretch, factor p. And here, p is on the outside. So it acts on y exactly as written. Multiply on the inside, f of qx, and it scales x, but reciprocally. With q equals 2, the curve is squashed horizontally to half its width. The peak slides from x equals 1 in to x equals a half. A coefficient of 2 inside gives a horizontal stretch of factor 1 over 2. Inside the function is the reciprocal. Q outside would be factor q, but q inside is factor 1 over q. That reciprocal catches people every single year. Now step back, because every single move we've made obeys one rule. And once it clicks, you never have to memorize a table again. Look at where each change sits relative to the function at f. Anything outside f, added on, or multiplying the whole thing, acts on y, and it does exactly what it says. Plus b goes up by b, times p stretches by p. A minus flips top to bottom. Outside is honest. Anything inside f, tucked in with the x, acts on x, and it does the opposite, or the reciprocal. Minus inside moves right, not left. A factor of q inside stretches by 1 over q, not q. And a minus inside flips left to right. The reason is always the same. To hit a given output, you must undo whatever's done to x first. So the effect reverses. Outside as written, inside opposite. That's the whole of 2.11 in one line. In the exam, you'll usually apply several transformations at once. So the key question is, does the order matter? Here's the clean answer. If two moves act on the same side of f, both on the outside or both on the inside, then order matters, because they're two operations on the same variable. And like adding, then doubling versus doubling, then adding, you get different results. But if the two moves act on different sides, say one stretches y and the other shifts x, they never interfere, and you can do them in either order safely. So the practical rule is simple. Watch out whenever several things happen to y together, or several things to x together. We'll see exactly this bite in the worked examples, particularly a vertical stretch combined with a vertical shift. Let's build a ladder of examples. Easy to hard, all my own. Part 1. Describe two single transformations. First, f of x plus 3. The plus 3 is outside f, so it acts on y as written. A translation up 3 units. In IB, you'd state it as a translation by the vector 0, 3. Now f of x minus 2. The minus 2 is inside, next to x, so it does the opposite of how it looks. Not left 2, but right 2. A translation by the vector 2, 0. Say the direction clearly. That's exactly what the MarkScheme wants. Part 2. describe minus f of x, 2f of x, and f of 2x. These are the reflection and stretch types. Minus f of x. The minus is outside, so it reflects in the x-axis. The hill becomes a valley. 2f of x. The 2 is outside, multiplying y, so it's a vertical stretch of factor 2, twice as tall. And f of 2x. The 2 is inside, on x, so it's a horizontal stretch of factor 1 over 2, half as wide. Notice the split. The same number, 2, gives factor 2 outside, but factor a half inside. Always name the axis and the factor. Both are worth marks. Part 3 connects straight to the quadratic vertex form from 2.6. Given f of x equals x squared, describe g of x equals 2, bracket x minus 1 squared, plus 3, as a sequence of transformations. The vertex form isn't just algebra. It's a recipe of transformations, sitting right there in the brackets. Read it from the x outwards. Inside the bracket, x minus 1. That's inside, so write 1. Then the 2 multiplying the bracket is outside. A vertical stretch, factor 2. Finally, plus 3, outside, up 3. So g is x squared, moved right 1, stretched vertically by 2, then up 3. And its vertex sits at 1, 3. Reading the vertex form as transformations is the fastest way to sketch any quadratic. Part 4 is a classic short exam question, and it shows the rule paying off instantly. A point 2. 5 lies on y equals f of x. Find where it moves to under y equals 3f of x minus 1 minus 2. The trick: treat the x part and the y part separately. The x-coordinate is governed by what's inside f. There we have x minus 1. Inside, so shift right 1, and the x value 2 becomes 3. The y-coordinate is governed by everything outside f, applied as written. Multiply by 3, then subtract 2. So 5 becomes 3 times 5 minus 2, which is 13. The image is the point 3, 13. Inside handles x, outside handles y. 2 tiny sums, done. Part 5 drives home why order can matter. And it's the single most common place students lose marks. Take 1 point, 0, 1, and apply 2 transformations that both act on y. A vertical stretch of factor 2, and the translation up 3. Watch what happens when we swap the order. Order A, stretch first. 0. 1 doubles to 0, 2, then plus 3. Lifts it to 0. 5. Order B, add 3 first. 0, 1 goes up to 0, 4, then doubling sends it to 0, 8. Because the doubling now acts on the 3 as well. 5 is not 8. Same 2 moves, different order, different graph. Both act on y, the same side of f, so they fight over it. When you describe a composite, state the order. And by convention, apply inside then outside operations carefully. Now the exam graph, other channels skip. The master key, worth repeating out loud in the exam. Inside is x, and does the opposite, or reciprocal. Outside is y, and does exactly what it's written. Get that one sentence solid, and every question here collapses to bookkeeping. 4 rules to bank. 1. Chant inside equals x equals opposite, outside equals a y as written. 2. If a direction ever feels slippery, check with a single point. Track where it lands, and the ambiguity vanishes. 3. On paper 2, graph the original and the transformed function together on your GDC to verify before you commit ink. And 4. The quadratic vertex form is literally a transformation of x squared. Write h, stretch a, up k. And the very same shifting and stretching move. Exponential and log graphs. So this one skill pays off across the whole course. Finally, the 3 traps that quietly cost marks. 1. Reading f of x minus a as a shift to the left. It's inside, so it's the opposite. It moves right. This is the #1 error in the whole topic. 2. Calling f of 2x a stretch of factor 2. Inside is the reciprocal, so it's a horizontal stretch of factor 1, half. The curve gets narrower, not wider. And 3. Applying a vertical stretch and a vertical shift, in whatever order feels easy. They act on the same side, y, so the order changes the answer, as our 0.5 versus 0.8 example showed. Dodge these 3, and 2.11 is free marks. And that is SL 2.11, fully covered. And with it, topic 2, functions, is complete. You can now take any curve and translate it, reflect it, or stretch it. Read a transformation straight off an equation, and apply a sequence in the right order. Remember the one rule. Outside the function, acts on y as written. Inside acts on x, the opposite, reciprocal way. Next, we open a whole new topic, geometry and trigonometry, starting with 3-dimensional space. For more, that's markscheme.app. See you in topic 3.